Spring 1942, Aberdeen Proving Ground, Maryland. Lieutenant Colonel Alvin Barber and his team of American engineers stood in stunned silence, staring at the Soviet T-34 tank that had just been unloaded from a cargo ship. This was the tank that had terrified German Panzer crews. The wonder weapon that Guderian himself had called superior to anything Germany fielded. The machine credited with stopping the Wehrmacht cold outside Moscow. Barber walked slowly around the 30-ton beast, running his hands along the hull. Then he stopped. His fingers had found the welds. Not the smooth, precise welds American and German tanks used. These were rough, uneven, almost agricultural, like someone had learned to weld yesterday and didn't care about aesthetics. "Get me a metallurgist," Barber said quietly, "and a psychiatrist, because either the Soviets are insane, or we've been doing this completely wrong." For the next 3 months, American engineers would tear apart this T-34, examining every component, testing every system, measuring every tolerance. What they discovered would shatter every assumption Western military planners held about weapons engineering. The T-34 wasn't just crude. It was deliberately, systematically, brilliantly crude. And that crudeness was precisely why it was winning the war. Before we reveal how garbage welds beat precision engineering, pulverize that subscribe button. Like and comment if you think you could build better tanks than trained engineers. This channel exposes why good enough often beats perfect. Now let me show you how Soviet crudeness defeated German sophistication. The first thing that struck Captain James Morrison, a metallurgical engineer from Detroit's automotive industry, was the welding. He'd been examining tank armor for 2 years, analyzing German plate, British castings, American rolled homogeneous armor. He knew what quality welding looked like. The T-34's welds looked like sabotage. Rough, uneven, with visible slag inclusions and porosity. Welds that would have gotten a factory worker fired from any American plant. "This is unacceptable," Morrison said, running his fingers along a hull seam. "These welds are structurally compromised. Look at this, you can see gaps, inclusions, surface irregularities. This tank should have cracked apart under combat stress." He pulled out his measurement tools and began documenting the defects. Every weld he examined showed the same pattern. Fast, rough, barely adequate by American standards. But then Morrison did something that would change his entire understanding. He requested combat reports from Soviet forces. How many T-34s had suffered catastrophic weld failures in combat? The answer shocked him: virtually none. Tanks hit by anti-tank rounds sometimes had welds fail near the impact site, but spontaneous weld failures were almost non-existent. These terrible welds were holding up under conditions that should have shattered them. The armor plate itself presented another puzzle. American engineers used carefully controlled heat treatment to achieve specific hardness values with minimal variation. The T-34's armor showed hardness values that varied wildly. Some sections tested at 290 Bernal hardness, others at 370, all on the same plate. In American manufacturing, this would indicate catastrophic quality control failure. Entire production runs would be rejected for such inconsistency. Master Sergeant Thomas Riley, who'd worked at Chrysler's tank arsenal for 3 years before joining the Army, examined the hull construction with growing bewilderment. "They're not even trying for precision tolerances," he reported during the first week's briefing. "Look at these plate fits, gaps of 2 to 3 millimeters in places. We'd reject this as scrap. But somehow it's holding together." The glassy plate, the sloped front armor that gave the T-34 its revolutionary protection, was a single massive casting. American engineers marveled at the casting technology while simultaneously being horrified by the execution. The casting had visible porosity, rough surfaces, and dimensional variations that would never pass American inspection standards. Yet ballistics testing would later prove this crude casting more effective than carefully machined rolled plate. Lieutenant Frank Chen, a mechanical engineer from MIT who'd been commissioned directly into the Ordnance Corps, spent days examining the suspension system. The Christie suspension that gave the T-34 its legendary mobility used large road wheels mounted on coil springs. But the execution was brutally simple. No sophisticated shock absorbers, no precision bearings, just large coil springs and basic pivot points. This is 1920s technology, Chun said, shaking his head. We abandoned this level of simplicity years ago. These springs are just springs. No damping, no sophisticated rate control, nothing. It should ride like a buckboard wagon. But when they test drove the T-34 across Aberdeen's rough terrain, the ride quality was surprisingly good. The massive springs absorbed impacts through sheer brute force, compensating for lack of sophistication with raw mechanical advantage. The transmission examination began with optimism that quickly turned to disbelief. Sergeant Howard Matthews, who designed gearboxes for International Harvester before the war, removed the inspection covers and stared inside with an expression somewhere between confusion and horror. "This is a 4-speed gearbox," he announced. "For speeds. We abandoned 4-speed transmissions for tanks 3 years ago. And the gear teeth, look at these teeth. They're straight cut, wide, with enormous tolerances between components. American tank transmissions used synchromesh gearboxes with helical cut gears for smooth, quiet operation. The T-34's transmission used straight-cut gears that would have been at home in a 1925 farm tractor. The gear teeth were thick, crude, with none of the precision machining that characterized American or German gearboxes. When they test-operated the transmission, it made grinding, whining noises that would have sent any American tank back to the depot for overhaul. But Matthews discovered something remarkable during durability testing. The CRUDE transmission that looked like it would fail immediately just kept working. They ran it for 500 kilometers, then 1,000, then 2,000. The transmission that American engineering principles said should have destroyed itself within hours was still functioning after abuse that would have shattered sophisticated American gearboxes. "I don't understand," Matthews admitted during a progress briefing. "Everything I know about transmission design says this shouldn't work. The tolerances are too loose. The gears are too crude. The synchronizers are non-existent. But it works, and it keeps working." He paused, struggling with the implications. Maybe everything I know about transmission design is wrong. Or maybe the Soviets know something we don't. The engine presented an even more dramatic contradiction between sophistication and crudeness. The V2 diesel was theoretically advanced. A 38.8-liter V12 aluminum block diesel engine producing 500 horsepower. Diesel engines in tanks were revolutionary. Most nations used gasoline engines despite the fire risk. But the execution of this sophisticated concept was shockingly crude. Captain William Parker, an engine specialist from General Motors, led the power plant examination. "The aluminum castings are terrible," he reported. "Porosity throughout, rough surfaces, inconsistent wall thicknesses. The cylinder liners are just pressed in, no sophisticated retention system. The fuel injection is basic mechanical injection with no precision timing control. This engine looks like someone described a diesel engine over the phone to a farmer who then tried to build one in a barn. The fuel filters were particularly alarming. American engines used sophisticated multi-stage filtration to protect precision injection systems. The T-34's fuel filter was a simple mesh screen that would barely stop large particles. "This filter won't protect anything," Parker said. "Dirt will get through, damage the injection pumps, score the cylinders. This engine should last maybe 100 hours before catastrophic failure." They ran the engine. 100 hours, 200 hours, 500 hours. The engine that should have destroyed itself kept running. Parker began taking oil samples, analyzing where metals, examining components for damage. What he found contradicted everything he knew about engine design. Yes, the crude filtration was allowing dirt into the engine. Yes, components were wearing faster than American engines. But the wear was distributed across overbuilt components that could absorb the damage. The Soviets aren't trying to prevent wear, Parker realized during week 3. They're designing for wear. These components are so overbuilt that they can lose 30 to 40% of their material to wear and still function. It's not precision engineering, it's brute force engineering. They're accepting that parts will wear out and designing so that worn parts still work. This philosophy manifested throughout the engine. The pistons were aluminum castings with enormous clearances when new, clearances that would cause any American engine to burn oil and lose compression. But after 500 hours of wear, Those clearances reached optimal dimensions. The engine actually ran better after wearing in than it did new. American engines were designed to tight tolerances that degraded over time. Soviet engines were designed to loose tolerances that improved through initial wear. The tracks represented perhaps the most dramatic example of Soviet design philosophy. American engineers used precision-cast track links with hardened pins and sophisticated bushings. Each link was a precision component requiring specialized manufacturing. The T-34's tracks were stamped steel plates held together with simple pins. No bushings. No sophisticated retention systems. Just steel plates and pins. Lieutenant Sarah Mitchell, a materials engineer from Bethlehem Steel, examined the tracks with mounting frustration. "These are garbage," she declared. "Look at this, the pins are just mild steel rods. No heat treatment, no special alloys, nothing. These should wear out in 500 kilometers. The tracks should be falling apart." She measured the pin diameters, calculated load factors, and predicted catastrophic failure within days. The tracks lasted 3,000 kilometers during testing. Mitchell couldn't understand it until she examined worn pins from Soviet tanks captured in combat. The pins did wear rapidly by American standards, but they were so oversized initially that they could lose 40% of their diameter through wear and still hold the tracks together. When pins finally wore out, replacing them required no special tools. Any piece of rod stock of approximately the right diameter would work. "They're not building tracks," Mitchell realized. "They're building disposable assemblies that anyone can replace with primitive tools. It's not engineering, it's, I don't know what to call it, anti-engineering, deliberate crudeness." The concept violated everything she'd learned at engineering school, yet it worked flawlessly in practice. The gun sight presented another shocking example. American tank sights used precision optics with sophisticated reticles and range-finding mechanisms. German sights were even more advanced, with temperature compensation and elevation adjustment systems that required specialized training. The T-34's sight was a simple telescope with a crude reticle etched onto glass. No sophistication, no advanced features, just basic magnification and a crosshair. Captain Robert Morrison, an artillery officer who trained on American gun sights, test-fired the main gun using the crude optics. "This sight is terrible by our standards," he reported. "The magnification is low, the reticle is imprecise, the field of view is narrow. But..." He paused, reviewing his accuracy data. "But it works. At combat ranges under 1,000 meters, this simple sight delivers adequate accuracy. And unlike our sophisticated sights, this one won't misalign if the tank takes a hit. It won't need recalibration. It won't fail from shock or vibration." The turret rotation mechanism revealed the Soviet philosophy in its purest form. American tanks used electric traverse motors with variable speed control, allowing precise gun laying and smooth target tracking. The T-34 used a manual traverse system, pure muscle power turning gears to rotate the turret. No electric motors. No power assistance, just the gunner cranking a hand wheel. "This is primitive," Lieutenant Colonel Barber said during a demonstration. "The gunner has to manually traverse 45 tons of turret. In combat, when you need to quickly engage a target that appears on your flank, this manual system could be fatal. The delay between target acquisition and engagement is unacceptable." He sat in the gunner's position and attempted to quickly traverse the turret 90 degrees. It took 38 seconds of hard cranking. But Sergeant Matthews, who'd been studying Soviet tactical doctrine, offered a different perspective. "Sir, Soviet tanks don't fight the way we do. They don't do precision gunnery with careful target tracking. They maneuver aggressively, close range rapidly, and engage targets in quick succession at close range. In that tactical context, the manual traverse is adequate. And unlike electric systems, it never breaks. Never needs electrical troubleshooting. Never fails when you need it most." The ergonomics were equally crude. The crew compartment was cramped, uncomfortable, and poorly ventilated. The commander's cupola offered limited visibility. The driver's position was nearly claustrophobic. American tankers testing the vehicle complained of fatigue, discomfort, and poor situational awareness. Everything about the interior seemed designed to make the crew's life miserable. Yet Soviet crews fought effectively in these machines. The Americans began to realize that the Soviets had made a conscious trade-off: crew comfort versus mechanical simplicity. A sophisticated ventilation system required ductwork, fans, and electrical components that could fail. The T-34 had minimal ventilation, but also minimal systems that could break. Uncomfortable crews were still effective crews. Dead crews whose sophisticated systems had failed were not. The ammunition storage exemplified this brutal pragmatism. American tanks carefully protected ammunition in armored bins with blast doors and blowout panels. The T-34 stored ammunition around the fighting compartment in simple racks. If the tank was penetrated, the ammunition would likely explode, killing the crew. American engineers were horrified by this apparent disregard for crew safety. But Captain Morrison discovered the twisted logic behind this design. "They're not disregarding crew safety," he explained. "They're accepting that if the armor is penetrated, the crew is probably dead anyway. So why add weight, complexity, and cost for sophisticated ammunition protection that only matters if you've already been penetrated? They're optimizing for not being penetrated in the first place: thick sloped armor, small target profile, high mobility." The maintenance philosophy revealed perhaps the most profound difference between Soviet and Western design thinking. American tanks came with detailed maintenance manuals requiring specialized tools and trained mechanics. A proper Sherman maintenance required 50 pounds of specialized tools. The T-34's maintenance manual was remarkably simple, and most procedures could be performed with basic tools: hammers, wrenches, pry bars. Sergeant Riley demonstrated this during a maintenance exercise. He was given a T-34 with a deliberately damaged road wheel and basic tools: a sledgehammer, 2 wrenches, and a pry bar. "This is all a Soviet field mechanic would have," Barber explained. Riley approached the problem with American thinking, looking for proper removal procedures and specialized equipment. After 20 minutes of frustration, he simply started hammering. The damaged wheel came off. A replacement wheel was hammered into place. Total time: 12 minutes. Riley stood back, staring at the repair with a mixture of admiration and horror. "That's not how you're supposed to repair tanks," he said. "But it worked. And any conscript with minimal training could do what I just did. You don't need skilled mechanics. You don't need specialized tools. You just need basic understanding and a hammer." This hammer maintenance philosophy extended throughout the tank. Track replacement didn't require specialized track tools, just sledgehammers and pry bars. Engine maintenance didn't require precision measurement tools, just basic wrenches. Even the fuel filters, despite being crude, could be cleaned by anyone with 5 minutes of training. The T-34 had been designed from the ground up to be maintained by minimally trained workers with minimal tools. The American team began examining Soviet manufacturing context. Intelligence reports revealed that Soviet tank factories employed largely unskilled labor. Peasants pulled from collective farms, housewives, teenagers. These workers had no manufacturing experience, no technical training, no engineering background. They were taught to perform specific tasks: weld this seam, cast this component, assemble these parts. The tasks were deliberately simplified so that minimal training produced adequate results. Captain Parker spent a week analyzing this manufacturing philosophy. "We've been designing tanks for skilled workers to build and skilled mechanics to maintain," he concluded. "The Soviets are designing tanks for unskilled workers to build and semi-literate conscripts to maintain. That's why everything is so crude. It has to be crude enough that someone with minimal training can make it work." The welds that Morrison had initially dismissed as sabotage suddenly made sense. They weren't bad welds by accident. They were deliberately rough welds made by workers with minimal welding training. But the Soviet designers had engineered the joints so that even rough welds provided adequate strength. The design compensated for crude manufacturing by overbuilding everything. This revelation extended to the armor inconsistency. American factories carefully controlled heat treatment to achieve precise, consistent hardness values. Soviet factories didn't have the sophisticated temperature control equipment or trained metallurgists to achieve that consistency. So Soviet designers had simply specified wider, acceptable hardness ranges. Some sections harder, some softer, but the overall protection adequate despite inconsistency. The track pins that wore so rapidly also made sense in this context. Precision-hardened pins required sophisticated heat treatment facilities and skilled metallurgists. Simple mild steel rods required neither. Yes, they wore out faster, but they were also infinitely easier to manufacture in factories staffed by unskilled workers. And when they wore out, they could be replaced by workers with no training using tools available anywhere. Lieutenant Colonel Barber called a comprehensive briefing in June 1942 to present the team's findings. The conference room at Aberdeen filled with ordnance officials, intelligence officers, and industrial representatives. Everyone wanted to understand the Soviet tank that was supposedly winning the war on the Eastern Front. Barber's opening statement stunned them. "Gentlemen, the T-34 represents the most sophisticated application of crude engineering principles I've ever encountered." The phrase made no sense to the audience. Sophisticated crudeness. Barber continued, "We've spent 3 months examining this tank from the perspective of American engineering standards. By those standards, virtually everything about the T-34 is inadequate, substandard, or outright defective. But those standards are the wrong lens for understanding this machine. The T-34 has been designed to solve problems we don't have and succeeds brilliantly at solving those problems." He presented the data methodically. American tank factories employed skilled workers, had sophisticated machinery, maintained tight quality control, and produced tanks requiring trained mechanics for maintenance. Soviet factories employed unskilled workers, had limited machinery, maintained loose quality control, and produced tanks requiring minimal training for maintenance. "We're comparing apples to oranges," Barber explained. "Or more accurately, we're comparing precision instruments to agricultural equipment. They're designed for completely different contexts." The ballistic testing results shocked everyone. Despite crude armor with inconsistent hardness, the T-34's sloped glacis plate provided protection equivalent to or better than much thicker vertical armor on German tanks. The 60 mm glacis at 60 degrees was effectively 120 mm against most incoming rounds. American engineers had understood sloped armor theoretically but hadn't implemented it aggressively because sloped armor created interior space problems. The Soviets had simply accepted cramped crew compartments as the price for superior protection. The mobility tests revealed another area where crudeness translated to superiority. The wide tracks, 640 mm compared to Sherman's 420 mm, distributed weight over a larger area, giving the T-34 ground pressure of just 0.64 kilograms per square centimeter. This allowed the tank to operate effectively in mud and snow conditions that immobilized more sophisticated American and German tanks. The CRUDE suspension system actually performed better off-road than sophisticated American systems because it was less susceptible to clogging with mud. Captain Morrison presented the maintainability analysis that would influence American tank design for decades. The T-34 achieved 70 to 90% operational readiness rates in Soviet service despite crude manufacturing and minimal maintenance. German Panthers achieved 35 to 45% operational readiness despite sophisticated engineering and extensive maintenance infrastructure. The difference is that the T-34 is designed to work despite neglect, while sophisticated tanks are designed to work with perfect maintenance. The production numbers told the ultimate story. Soviet factories produced approximately 1,000 T-34s per month in 1943 using largely unskilled labor in facilities that had often been evacuated and rebuilt. American factories produced similar numbers of Shermans but required skilled workers and sophisticated machinery. German factories produced 200 Panthers per month despite employing skilled workers and having superior manufacturing technology. The crudeness that seemed like a weakness was actually an overwhelming production advantage. The strategic implications became clear when American intelligence began receiving detailed reports from the Eastern Front. At the Battle of Kursk in July 1943, the largest tank battle in history, German forces deployed approximately 200 Panthers, their most sophisticated tanks with superior optics, precision engineering, and advanced armor. Soviet forces deployed over 800 T-34s, many of them earlier models with the 76 mm gun rather than the later 85 mm version. By German engineering logic, the 200 sophisticated Panthers should have achieved favorable kill ratios against the crude T-34s. The actual results told a different story. Of the 200 Panthers committed to battle, fewer than 50 remained operational after 5 days. Not all were destroyed by enemy fire. Many broke down from mechanical failures, transmission problems, final drive failures, and engine overheating. The Panthers that remained operational had indeed achieved impressive individual kill tallies, but operational readiness fell below 25%. The T-34 force, meanwhile, maintained 60 to 70% operational readiness throughout the battle. Yes, hundreds of T-34s were destroyed or damaged, but Soviet repair crews recovered damaged tanks overnight, hammered them back into functionality, and returned them to combat. The crude construction that American engineers had criticized as inadequate proved infinitely reparable under field conditions. Damaged Panthers required depot-level maintenance or were abandoned. Damaged T-34s were fixed with sledgehammers and returned to battle. Lieutenant Mitchell studied post-battle reports with growing appreciation for Soviet design philosophy. They're not trying to prevent damage, she realized. They're designing for damage. A T-34 hit by a non-penetrating round might have damaged road wheels, a thrown track, and damaged external components. But a crew with hammers and pry bars can fix most of that damage in hours. A Panther with similar damage needs specialized tools, trained technicians, and sometimes complete component replacement. The disposability principle extended beyond field repair. Soviet doctrine accepted that T-34s would be lost at high rates and planned accordingly. Replacement tanks flowed constantly from factories to the front. Crews who lost tanks received new tanks within days. The entire system was designed around the assumption that individual tanks were expendable. What mattered was maintaining numerical superiority and keeping the survivors operational. Captain Parker studied Soviet engine maintenance doctrine and found it shockingly simple. Change oil every 1,000 kilometers. Change filters every 500 kilometers. If the engine runs rough, adjust fuel injection. If it won't start, check fuel and electrical connections. That was essentially the entire maintenance program. No sophisticated diagnostics, no precision adjustments, no careful monitoring of dozens of parameters. Just basic maintenance that any semi-trained conscript could perform. This contrasted sharply with American and German maintenance doctrine, which required detailed inspection schedules, precise adjustment procedures, and extensive documentation. A Sherman needed 12 hours of maintenance per 100 hours of operation. A Panther needed 64 hours. A T-34 needed 4 hours. The crude design that required no precision maintenance was actually the most maintainable design. The implications for American tank design were profound but troubling. American industry was built around precision manufacturing with skilled workers. American military culture emphasized sophisticated technology and proper maintenance procedures. Could America adopt Soviet crudeness principles without abandoning these strengths? Should America even try? The final Aberdeen report, classified and distributed to senior ordnance officials in August 1942, contained conclusions that would influence American military thinking for decades. The T-34 represents a design philosophy fundamentally different from Western engineering traditions. Colonel Barber wrote, "It prioritizes operational effectiveness over mechanical perfection, field maintainability over manufacturing precision, and quantity production over individual quality. By every traditional metric of engineering excellence, the T-34 is inferior. But by the only metric that matters in war, combat effectiveness, it may be superior to anything we or the Germans have produced." The report's most controversial recommendation was that America should selectively adopt some Soviet principles. Not the crudeness itself, but the underlying philosophy. Design for the weakest link in your production and maintenance chain, not the strongest. Build tanks that average mechanics can maintain, not tanks that require specialists. Accept adequate performance achieved reliably over perfect performance achieved rarely. These recommendations faced fierce resistance from American ordnance officials and tank manufacturers. The suggestion that America should learn from Soviet crudeness seemed to insult American engineering capability. But the data was irrefutable. T-34s were winning the war on the Eastern Front through availability and reliability, not through mechanical sophistication. Germany's increasingly sophisticated tanks were losing despite superior engineering because sophistication had become a liability, Lieutenant Colonel Barber's final assessment would be quoted in military engineering courses for the next 80 years. The Soviets have solved a problem we didn't know existed. How do you build weapons when your workforce is unskilled, your factories are primitive, your maintenance infrastructure is minimal, and your combat conditions are brutal? The answer is you design for crudeness. You make crudeness itself a design feature rather than a defect. The T-34 is crude by our standards because crude is what works in Soviet circumstances. The Korean War would provide the ultimate validation of Soviet design philosophy. When American forces examined T-34 divided by 85s captured from North Korean and Chinese forces in 1950 to 1953, they found tanks that had been in continuous service for 5 to 10 years, often with minimal maintenance, still functioning effectively. Many showed signs of crude field repairs, welded patches, improvised parts, components that clearly weren't original equipment. But they still worked. One captured T-34 examined at Aberdeen in 1951 had a transmission that analysis revealed wasn't factory original. The gears showed machining marks indicating manufacture on primitive equipment. Intelligence concluded it was a field-fabricated replacement, probably made in a Chinese maintenance depot with basic machinery. American transmissions required precision manufacturing that couldn't be replicated in field conditions. Soviet transmissions were crude enough that barely adequate facilities could produce functional replacements. The production numbers told the ultimate story of crude effectiveness. By war's end, Soviet factories had produced over 84,000 T-34s in various models. This staggering number was achieved despite factory evacuations, unskilled labor, and primitive manufacturing conditions. Germany produced 6,000 Panthers despite superior manufacturing technology and skilled workers. America produced 49,000 Shermans despite having the world's most advanced manufacturing infrastructure. The T-34 achieved this production superiority precisely because of its crudeness. Unskilled workers could build it. Primitive factories could manufacture it. Minimal tooling could produce it. The very characteristics that made American engineers recoil in horror were the characteristics that made it mass-producible in Soviet conditions. Captain Morrison, reflecting on the investigation years later, wrote, "We examined the T-34 expecting to find sophisticated engineering disguised as crudeness. Instead, we found crude engineering that was sophisticated precisely because of its crudeness." The Soviets had understood something profound. In total war, the adequate weapon you can build 100,000 of beats the perfect weapon you can build 10,000 of. Crude beats sophisticated when crude can be mass-produced and sophisticated cannot. The legacy of the Aberdeen T-34 evaluation extends beyond tank design to influence military procurement philosophy worldwide. Modern military planners still reference the T-34 principle, that reliability, maintainability, and mass production capacity matter more than individual technical superiority. The most sophisticated weapon that doesn't work or can't be produced in adequate numbers is worthless. The crude weapon that works reliably and exists in overwhelming numbers wins wars. The American engineers who'd initially been horrified by the T-34's rough welds, crude castings, and agricultural simplicity came to view it with grudging admiration. They had learned that engineering excellence isn't defined by precision or sophistication, but by effectiveness in intended context. The T-34 was excellent engineering precisely because it matched its design to Soviet manufacturing capabilities and combat requirements. The captured T-34 at Aberdeen remained in storage for decades, eventually finding its way to the U.S. Army Ordnance Museum. It sits there today, its rough welds and crude components preserved as testimony to a profound truth. Sometimes the best engineering solution is the simplest one that actually works. The tank that American engineers initially dismissed as barely adequate had helped defeat Nazi Germany, fought in Korea, and influenced tank design worldwide. In the end, the investigation revealed that Soviet engineers hadn't built a crude tank because they couldn't build a sophisticated one. They'd built a crude tank because crude was exactly what they needed. They'd solved the right problem, how to win a war with limited resources, rather than the wrong problem, how to build the most technically impressive machine. That distinction, more than any technical specification, explained why 84,000 T-34s defeated 6,000 Panthers. Sometimes crude beats sophisticated. Sometimes simple beats complex. Sometimes adequate beats perfect. The T-34 proved all three truths simultaneously, teaching lessons that Western engineers are still learning today.